Okay, so we're recording the video. Yeah, so here we go. We want to talk about analytic mechanics. We have a lot of stuff on the agenda. We're going to talk about the syllabus. There are some logistics. We're going to talk about exam dates, homework assignments, things like that. Before we do that, because that's kind of the mundane tedium, so to speak, let's talk about the exciting physics. So we'll start this meeting talking about some exciting physics and to get us off on a good note, and then we'll return to some logistics things we have to deal with in terms of the course and grading and things like that. Okay, we're going to start, and what I'm going to do here is click the share screen button. I hope this works. Again, I'm in the new world of Zoom 5.1. I'm going to share the screen, and then I hope to get my presentation, which I have prepared. So here we go, share screen. I clicked it. Ooh, look at that. All these options. We're going to start. Hey, this 5.1 is not so bad. Yeah. Look at that. Okay. Now the windows, it's certainly doing some funny things. I'm going to try to move the chat window. Okay. Well, I hope you can see these slides. Let's do this. Let me try to recover my chat window. If anyone can see the Interplanetary superhighway, could you type something into the chat window? Something like, yes, I can. There, yeah, oh, this is great. We can see it. Okay, wow, that's great. Wonderful. Yeah, okay. Now, let me ask you this as a follow-up question. Unfortunately, on my screen, there's some clipping. I can't see a couple of inches of screen on the right. Can you see the whole thing, or are you getting clipped on the right? Okay, great, great. So it's just me? Okay, wonderful. Yeah, this is fantastic. Okay, so let's talk about this. The point here is, as we go through the course, we're going to be talking about opportunities to apply this wonderful subject to current research. There are some fascinating research areas. And these slides are prepared by Kathleen Howell. She's a professor at Purdue University. And this is a wonderful set of slides that we'll talk about today to some degree. And then later in the course, we're going to revisit these slides. There are some fascinating things going on in the slides. We will also look for opportunities to talk about applications to industry. Okay, some of you, the question is, when you walk out of here with your diploma, what are you going to do? Well, some people go to academia, some people go to industry, and other people choose to do other things. Obviously, they're all good choices. So we'll make some remarks also on applications to industry. Okay, so the interplanetary superhighway. This is a fascinating topic, and our story begins, I like to begin the story with kind of a Berkeley perspective. Just across the street from our physics building, we have the math building, Evans Hall, chock full of world-class mathematicians. And a few years ago, they used advanced mathematics to save a spacecraft. This was a spacecraft launched by a different space agency, not NASA. It was a space agency of a different country. The spacecraft was stranded with insufficient fuel to get to the moon. And these mathematicians used some advanced methods, kind of related to what we're going to talk about in our course. In our course, we're going to set the foundations for all of this. And they saved the spacecraft using advanced mathematics. Okay, so it's not too often that you have a bunch of mathematicians saving the day and doing this in an exciting kind of science fiction environment almost. So this was the beginnings of the study of the interplanetary superhighway. The point is, if you have a robotic spacecraft, you can find ways to get to your destination that are highly non-intuitive. And this picture here is kind of, this first slide here shows you the interplanetary superhighway. And it's kind of schematic here. It's a depiction in a three-dimensional space of these tubes. And you have these ribbons that go winding around the tubes, okay? This is kind of a three-dimensional depiction of the interplanetary superhighway. Actually, we're going to have to think in higher dimensional spaces. We're going to be taking a journey into some higher dimensional spaces to understand this interplanetary superhighway. Let's skip to this slide here. Yeah, you can see this is from the good old days, a long time ago. It was 1982. This diagram here, again, I'm a little bit challenged because of what they did to me with Zoom 5.1. I can't see the whole picture, but I hope you can, and based on the chat window, I think you can. Look at this. I would say it's fair to say that this is a highly non-intuitive orbit. If you want to get your spacecraft to this comet Giacobini-Zener, comet Halley, this is very non-intuitive. Let me see if I can, what if I click on this triangle? Nope, that didn't do it. I want to see more of this thing. I don't think it's going to let me. Okay, I can move this chat window over a little bit. Okay, so the point is, we're going to use analytic techniques. Now, in those days, they computed these things, quote, by hand. Of course, they used a computer, but they were not guided by the advanced mathematical knowledge that has emerged over recent decades. So that's one of the points here. There continues to be interesting research done in this field. So this was a voyage. Let me just scroll down. Today, we're just going to look at an overview of these slides to just capture what an amazing topic this is. And we'll talk about stable and unstable manifolds. Okay, so stable and unstable manifolds. Again, I'm guilty of flipping through the slides too quickly. I admit that freely. I'm flipping through the slides very quickly because our purpose today is not to go through these slides in detail. We want to just get an overview of the amazing world of analytic mechanics alive and well today for research topics. So we're going to start talking about Lagrange points. In your Physics 7a BC and Physics 5a BC, you most likely talked about Lagrange points. We're going to be interested in stability. Okay, stable. In the upper left of this slide, I'll read some text. L1 stable manifold. Okay, L1 stable manifold. L1, that's one of the Lagrange points. There are quite a few Lagrange points, and according to tradition, they are numbered. And L1 is one of the Lagrange points, traditionally called L1. There are going to be stable and unstable manifolds. We're going to talk about stable and unstable manifolds. The word stability here is crucial. Okay, think of a traditional pendulum. Okay, and here when we say pendulum, rather than a massive object suspended by a string, we need to have it suspended by a rigid rod. And the reason is we're going to explore very large angles. For small displacements away from the lower equilibrium, you could have used a string. It's a popular choice. It works just fine if you want to explore the equilibrium there at the bottom, and that's a stable equilibrium. If the pendulum is pushed away from the equilibrium point, it oscillates about the equilibrium point. Now, if you build this pendulum with a rigid rod, you can explore a different equilibrium. This is when you rotate the whole thing 180 degrees so that the mass is above the point that is fixed. That's an equilibrium. If you balance it perfectly, which is possible in classical mechanics, then it'll stay there. It's an equilibrium, right? All the forces are balanced. But a tiny excursion away from that equilibrium point results in exponential growth. That's an example of an unstable equilibrium, okay? All of this can be revisited in higher dimensional contexts, and so we'll talk about stable and unstable manifolds. Okay, so our purpose here, again, we're just enjoying some of the exciting topics that lie ahead. Let's go ahead to the end of this presentation. They actually want to recruit you. Okay, and here's the recruitment poster. We want you. These authors are advocating a station located at the L1 gateway. They envision this to be a gateway to launch robotic spacecraft. It's appropriate for robotic spacecraft, not so appropriate for human space flight because you may have to wait 3 months to get to your destination or longer. And that's not good for people like us that like to breathe air and eat food and stay alive. You know, that's a challenge. But for robotic spacecraft, this stuff is perfect. Okay, let's look at another document here. Now, do I have to tell it to, okay, I think I'm gonna play it safe here. Okay, I clicked the stop share button. Now I'm going to click the share button again to share a different document because I know this is a method that will work. Okay, this is a paper written by Martin Lowe and others. Okay, JPL, the Jet Propulsion Laboratory, Caltech. If any of you are in the Los Angeles area, I'd recommend stopping by there. I went to a conference at Caltech some years ago. Wonderful place. I really enjoyed it. So here in the lower right, there's a picture of Martin Lowe. Again, my screen is getting cropped, but I hope you can see it. So he's an expert here, and they have researched some very fascinating topics here. Again, I'll skip to the first page. Again, this topic we have talked about, the interplanetary superhighway. And they've taken it up a notch here and even addressed the question of the origins of life. You could imagine organic molecules being produced in the outer parts of the solar system and traveling along very mysterious paths. Have a look at some of these fascinating pictures. This is why we need to talk about Python, and we'll talk about, you know, the program we'll do in Python. For some of these things, you want to analyze them on a computer. But we'll talk about how organic molecules could migrate throughout the solar system. Again, these fascinating orbits here. And this one, for example, you have the planets. The horizontal axis is measured in AU. That's an astronomical unit, right? The average distance from the Earth to the sun with an appropriate average. And of course, our Earth is here. I don't know if you can see the mouse pointer. We're at 1 AU. There's Jupiter, there's Saturn, Uranus, Neptune, etc., Pluto. And we're talking about stable and unstable manifolds. So this would provide a path. These organic molecules could move throughout the solar system, and we can even talk about the origins of life on Earth. So again, I apologize. Today we're looking at these slides and papers very quickly because I'm clicking stop share, because our purpose was to motivate this fascinating topic. Okay, so let's now, okay, actually I want to present one more thing, okay? Remember what I said, we're interested in applications to academia, to pure scientific research. We're also interested in applications to industry. Okay, now let me look at the chat window. Yep, things are looking good. I'm constantly looking at the chat window to see if anybody has typed a question. Let's talk about industry, right? Because some of you will go on to industry and do great things there. So let's talk about applications to industry. So just the other day, I was talking to a researcher in robotics, right? That's a fascinating, fascinating area to work in. And multi-fingered robots. If you build a robot, a really advanced robot, a multi-fingered robot, this robot can go around and grasp objects. It can pick objects up. It can do stuff that's really useful because it's a multi-fingered robot. We're going to talk about no-slip rolling conditions. This actually gets us right into some advanced mechanics. When you study the motion of an object, which is rolling without slipping, okay? This gets us into some fascinating advanced mathematics. So yeah, just the other day I was talking to a researcher in robotics, and his company, they work on a certain robotic system that has 6 degrees of freedom. So degrees of freedom, again, this is something we're going to study intensively this summer. Different textbooks define it differently. So we'll be careful to follow our textbook because our textbook is going to be a central reference point throughout this. We want to have a clear central reference point. And when we talk about exams, I'll tell you very clearly what's on the exams. The material for the exams will come from our textbook. And that's important to us so that we have a very clear statement about what material you need for the exams. I'll identify certain regions in the textbook which you need to study for the exams. Okay, so degrees of freedom. This is very important for robotics. Let's look at a fascinating, there was a presentation today at 11 o'clock. I could not attend because I was busy preparing my lecture, but I can tell you that many people I know went to this fascinating, I think it was done virtually, this fascinating presentation. So let me once again share the screen. I click here. Then I click on the thing that I'm gonna, this one. I click on this one, I click share. Okay, Manuela Veloso. Okay, Manuela Veloso gave a presentation. You see, it was today at 11 o'clock. And she reported on some fascinating things. She has 30 years in academia. And then she also, and we can scroll down here. So she has worked in robotics. Now this particular talk was on artificial intelligence. Okay, that's not so closely related to what we're doing today, but the robotics. In our course, we're going to talk about robotics, and we'll talk about mathematical methods. So this was a talk today, fascinating talk by Manuela Veloso, and I think it's another wonderful example of really interesting research, and we're talking about both academia and industry. Okay, so I like to provide these examples, these cutting edge examples. So we have our thumb on the pulse, so to speak. We're really in touch with current developments. I click on the stop share. Okay, so now again, the document camera is over here. I have, I've done all due diligence. I made the document camera a co-host. I also spotlighted the document. In Zoom, you can spotlight something, and I spotlighted it. So I hope you can see the document camera. Definitely let me know if you cannot see the document camera. And so we'll get to work here on some physics. Again, we will spend some time today talking about the syllabus and logistics, but first let's do some physics. Okay. All right. So in our studies of analytic mechanics, we're going to be very careful about the mathematical setting. Okay, so we'll start by talking about functions. Okay. To truly have a correct understanding of what we're doing, we have to identify the functions that are involved. So let's begin with a simple example of one-dimensional motion, and then we will compare that with some more complicated examples, higher dimensional examples. So first of all, here's our first example, one-dimensional motion. Okay, I'm trying to write this. This is our standard abbreviation. That's the numeral 1, and there's a capital D. 1D motion. So we have a particle moving along the x-axis. And of course, this is something you studied intensively in the Physics 7 sequence and the Physics 5 sequence. Let's draw a picture here. So there's our x-axis. Let's put the origin. Okay. We have the x-axis. The arrow is not very good. I better fix this. Okay. That's the x-axis. The positive x-axis is going to the right. So the function that emerges here, our notation now for the motion. In classical mechanics, our goal is to solve for the position as function of time, right? In quantum mechanics, it's different. You're going to solve for a wave function. But in classical mechanics, our goal, if it's a one-dimensional problem, we want to find this function x of t. So how can we visualize that? Remember, this is a picture of the physical space. Oops. Sorry, a little bit of a typo. I'm going to just kind of write over and let's call it good. That's the physical space, and I want to clearly delineate. Okay, so that's a picture showing us the physical space. How about the solution for the motion? Here we would draw a two-dimensional picture. Okay, so in general, the solution, this x of t, you should visualize a picture like this. Perhaps you have periodic motion centered about some point like this. Well, there's an example. Obviously, there are infinitely many different examples. Okay, so here we have to be very clear. The function, we write it like this. This x is the dependent variable. T is the independent variable. X is a function of time t. okay? When we read this, we say x of t, and that tells you that x is the dependent variable. The axis goes vertically here by tradition. The time is the independent variable. The axis goes horizontally like so. Okay, so now let's investigate some of the things we can do. If we have a solution like this, we can at least locally solve it. Okay. The point is, you see, we are approaching this in stages. We started with some rather elementary things that are very familiar to you from your introductory courses. Now, we can locally solve for t as a function of x. What does this mean? Well, I better get a colorful, let's see what we got here. Okay, so I've used some red color. It's a little controversial. Some users cannot see the color so clearly, but I hope it's clear that I used some red color. I colored one portion, and we're going to talk about branches and branch cuts. We can locally solve for t as a function of x, okay? And that means that we now have a vertical axis, the time t. Okay, and for that red portion now, it looks something like this. Okay, yeah, I can see why people would complain that red does not look very red. I think we can all agree the pen itself is very red, but the line on the paper not looking good, but you can see it's kind of reddish. Okay, but the point is, we cannot globally solve, right? We would have a multi-valued function. That's a term that's used. If I were to draw this, and I'll draw that kind of with dotted lines. Okay, so it's important that we compare and contrast here. We have these two pictures. The upper picture shows you x as a function of t, okay? This is a single valued function. For any value of the time t, you have a single value of x. So the term that's used here, that's a single valued function. If you talk about the global inverse, t as a function of x, you would have to look at this dotted line. This becomes a multi-valued function. For any value of x, for example, with this white pointer, I'm pointing to a location on the x-axis. For that value of x, if we invoke the notion of a function, it's a lookup process. We look to our curve, we would identify any point. So let's do that in pencil. For this point here, you would draw this vertical line. Okay, you identify all these intersections. Oh boy, you see I'm hurrying, and when I hurry, it starts to get sloppy. I need to calm down and quit hurrying and just draw the line correctly. It's right there. All right, there we go. Close enough for that one. Okay, so the picture that's emerging here is if we were to consider the entirety, of the original oscillating curve, we would have a multi-valued function. But the red color, remember the red color here, we've selected a portion locally. So I think it's useful to use the same red color here. You see what I did? The color really helps us to have some clarity. I use the same red color. I underlined the word locally. If you choose this portion here, you can invert that. That's this red curve here. And now you have a single valued function t of x. That's important to us. We're very interested in this function t of x. It turns out we can write down some interesting formulas for this function t of x. Okay, so let's return to our original picture and let's identify in our physical space. Suppose you choose 2 points. Okay, remember this picture shows you the physical space. The particle is moving in this one-dimensional physical space. We've chosen 2 points, x1 and x2, and we'd like to know how much time elapses traveling from x1 to x2. Okay, so travel okay, so that little arrow is not an X, it's just an arrow telling you that it's a symbol for this concept of traveling from x1 to x2. How much time elapses? Okay, so to compute how much time elapses, we're going to integrate from x1 to x2. We're going to integrate along the x-axis. We're going to add up differential contributions. So this is the most streamlined. You see, I've written an integral from x1 to x2 dt. You see, it's correct, but it's extraordinarily streamlined and compact notation. The notation is so compact and oversimplified that it's a little bit mysterious. What are we supposed to do? Integrate dt from x1 to x2. How are we going to do that? Okay, so let's have a closer look. Okay, so you see this is starting to make sense. What we have here is an integral. We're going to integrate from x1 to x2. Here's the differential. The variable of integration now is x. This is wonderful because you remember the picture, there was an x-axis. We're going to integrate from x1 to x2. The only remaining problem, we have to figure out what's dt dx. This had better make sense, and it really should be a function of x. If this is a function of x, life is wonderful. Well, there's some good news here. This is a function of x, and the reason is we're in this worldview now. We have t as a function of x. If t is a function of x, then what I'm going to do is a very dramatic arrow here. Okay. The pen was not up to the task. You see, it failed to deliver, but that's okay. We got an impressionistic. If t is a function of x, then the derivative dt dx is again a function of x. Now let's talk about the notation. We need to be a little bit pedantic about the notation. We really need to seize every opportunity to talk about the notation and make sure we understand the notation. Okay, so let's talk about this. Remember, when we say t of x, when you read this, you say t of x. T is a function of x. This is the picture. In your mind, you should have this picture. T is the dependent variable, x is the independent variable, and we're thinking of this red portion of the curve. Okay, it's a single valued function. The derivative is again a function of x. Okay, so this notation here, dt dx, we have explicitly exhibited the independent variable. When we write it like this, dt dx of x, right? Because throughout the course, there will be times that we use streamline notation. There will be times that we write it out very clearly. Okay, we have to understand both of those. So here, what we've written is the derivative dt dx, and these are ordinary d's. We're not doing partial derivatives. In a moment, we will be doing partial derivatives and we'll have different notation. But for ordinary derivatives, you have an ordinary, this is a regular little lowercase d. That's our notation for ordinary derivatives. dt dx is a function of x. Let's talk about different ways to write this. Again, there's only one mathematical concept here, the derivative of this function, okay? And it is a function of x. So now we want to emphasize that if you write it like this is perfectly correct and it's very clear. Sometimes you will see some authors write it like this, simply dt dx. Okay, these two are equal. When I say that, I'm emphasizing that we're writing the same thing using different notation. So in this upper form, we have dt dx. We've explicitly exhibited the fact that it's a function of x. Here we've suppressed it in the lower form. We just write dt dx. It's understood that it's a function of x. We've suppressed the argument. That means we're too lazy to write the argument. And the fancy terminology is we've suppressed the argument. Fine. Okay, now here's another one, and this is, it's going to start getting weird. we're going to have a very interesting foray into some notation here, and sometimes things will get weird. For example, this thing here, it's going to get weird in a moment when we write, this is an integral from x1 to x2 dx over x dot. Sorry, I went off the paper, but it's true, and we will justify this in just a moment, okay? We're integrating a function of x. The function is dt dx, which we're discussing here, all right? We're going to show that this function is the reciprocal of the time derivative. So yeah, this is getting a little bit weird. We're integrating dx over x dot, okay? And then we're going to do a shift in notation. Sometimes for the variable of integration, we'll put primes on there. So there will come a point where we're talking about dx prime over x dot. Yeah, it's possible to get bewildered, right? If you're integrating dx prime over x dot, yeah, things are starting to get weird. But don't worry, everything we're doing here is perfectly rigorous. The crucial thing is to understand the mathematical setting, and that's what we're doing here with these pictures. We have these, the mental pictures that you have here are crucial. So getting back to this one, dt dx, it's perfectly correct to write this as t prime. If you tell the reader, whoever's reading your paper that you're going to publish, that this is the usual prime denoting differentiation. There are other times we use a prime for different roles, but in this context, and there are many times we'll use a prime for differentiation, it's acceptable if you have a function of a single variable. And that's what we have here. T is a function of just one variable. It's a function of x. So t prime is the internationally agreed upon notation for the derivative of a single function. Okay, now there's a theorem that we're going to prove that this is the reciprocal, right? So all of this is just one wonderful thought bubble. I'm going to make it a rectangular thought bubble, but it's still a good thought bubble. We're talking about this dt dx. We're talking about different notation. We have to be very clear on the notation. Okay, so dt dx, it turns out it's the reciprocal. This is a good theorem, and we're going to talk about a couple theorems here. dt dx, I'm pointing to it with the pen here, is the reciprocal of dx dt. That may sound like a trivial theorem, but later today we'll talk about a related theorem, which usually comes as a real shock to people because there's a minus sign in there. Okay, so it's the reciprocal of dx dt. What does that mean? Well, it means you go back to this picture here. Here we had the function x as a function of the time t. At any location in this diagram, you choose a point, you can compute the slope. So we have a very clear intuitive picture for the slope. That's dx dt. Okay. Now, when you exchange the roles of the independent and the dependent variables, it's clear that the slope, right? You know, there's a theorem that if two lines intersect, then the product of the slopes is -1. Okay. Again, there's that minus sign we're going to talk about. But that's true quite generally for these two-dimensional diagrams. If you have two curves that intersect, if they intersect, sorry, I should have said if they intersect at right angles. Yeah, if you've got two curves that intersect at right angles, then the product of the slopes is -1. We're going to talk about that minus sign in just a moment. Let's continue our rectangular thought bubble here. So this is a well-known theorem, and here you can be sloppy. Remember, dx dt really comes to us from calculus. It's a special symbol for the limit of a certain difference quotient. That is, you form finite differences of delta x over delta t. That's a quotient. It's correct to talk about it as a quotient. But when you take the limit, you get a single number. That's dx dt. Dx dt is a single number. You shouldn't really separate the dx and the dt, but it's often done as in the ways to justify it. But the idea that dt dx is the reciprocal of dx dt, right? Really, that's a theorem. Now, let's complete our rectangular thought bubble here. Dx dt, in physics, we have very popular, this is wildly popular notation. Dx dt is called x dot. Okay, so that's it for our rectangular thought bubble. Notice we have had some interesting discussions here about notation and about the underlying concepts. We have to understand these functions. Okay, so what we're going to do here is integrate dx over x dot. Well, for a typical problem in mechanics, suppose you have a conserved quantity. Okay, so example, let's do an example here. All right. suppose you have a conserved quantity of the total energy. This is 1/2 the mass times x dot squared. There's the kinetic energy. And then you have some potential energy. Okay. You can solve this for x dot. There are two branches. You have to worry about the two signs. Let's choose the positive branch for the moment. Okay. So what we're going to do is form E minus U of x. Okay, so far so good. We're going to multiply by 2 over m. Okay, and then we'll take a square root. Okay, so this is important. It's important for homework 0, right? We've been talking about homework 0 and also for homework 1. But you see the structure that's emerging here. We can compute the time it takes to go from one location x1 to another location x2. And you see what you must do. You must integrate with respect to x. Okay, and you have this square root. The square root is in the denominator. And you see how everything makes sense now. It makes wonderful sense. This thing really is a function of x. This u of x is the potential energy. If it's a simple harmonic oscillator, that's a 1/2 kx squared, right? The energy stored in a spring, 1/2 kx squared. All right. So we'll move on to the next topic. Just a quick remark on notational weirdness. Suppose you wanted to investigate the time it takes. Remember the t of x. I'm going to squeeze it in here. I think I can do this. Okay. Again, everything we're doing here can be made rigorous, and you just have to look closely at all the concepts that we've talked about. So the time t to get to the location x, it's understood we're measuring relative to some starting point, so we're going to integrate for some reference point x naught up to the point x. Now you see we have to have a shift in notation. Earlier, we talked about an integral from x1 to x2. Those are two fixed points on the x-axis, and we integrated. Here's our variable of integration, x. So you see the dx there, and we're dividing by x dot. It's understood that x dot is a function of position, and this example here makes it very clear how x dot is a function of position. Okay, so we're going to leave this subject on the final, this will be the final kind of note here, and I want to emphasize this is a funny formula. Okay, let's, we're going to take a moment to sing the praises of this formula, and then we'll move on to the next topic. But you see what we've done. We've followed with this construction here, this integral from x1 to x2, right? The variable of integration was x, and the very compact notation for this denominator x dot, well, x dot is really the square root here. It is a function of x. That's what is important to us. It is a function of x. And of course, it's reciprocal as a function of x. So this is completely sane. This is 100% legitimate calculus. Now, here's where it looks funny. I mean, I think this is just a very amusing formula because you're integrating dx prime over x dot. If you tell someone about this formula, you know, they had better be prepared because this is shocking. What on earth does this mean to integrate dx prime over x dot? You see, we're pushing the limits of weird notation. But in fact, everything we've done is rigorous. The reason is we've chosen x as the limit of integration. It's completely legitimate, and we will often choose the limits of integration as we've done here. Notice the flow of logic. X is the independent variable of this function. T is the dependent variable. X is the independent variable. And here we're going to integrate from some reference location x naught to the location x. If we do that, we must use a different symbol for the variable of integration. It's customary to generate a different symbol that will play a role. Okay, in this case, we use x prime. This produces some new notation. We could have called it C. I personally would recommend using a different letter in a Greek. Look at that. That's a Greek lowercase c. I would favor this, but our textbook uses this. That's okay. We must learn to, appreciate other people's notation. And this is very common. It's customary to do this, to generate a new symbol. In this case, the prime is not a derivative. So I want to emphasize that here, because remember our rectangular thought bubble, this prime was a derivative. This prime is not a derivative. I think that needs to be stated very clearly. So not a derivative. That prime right there is not a derivative. It was just a means of producing a new symbol. And you can always tell by checking the units. This variable x prime has dimensions of meters. This variable x has dimensions of meters. This is not a derivative. Okay. This thing is a derivative. Oh boy.
I have a question, Professor.
But I did do it. Okay. That prime is a derivative. So the point here is we have to be very clear on the context, right? And sometimes when we prepare formula sheets, right, for what we're doing, our exams are going to be open book, right? So you don't have to prepare a formula sheet. You can if you want, but when you prepare formula sheets, you have to be clear on the context. And we'll have a lot of examples where if you take one formula from one part of the book, there will be a direct clash with the notation compared to a different part of the books. Oh, wait, we have a question.
Yes.
Yep, I see a question. Let's see, it was 1:24. So I am only 1 minute late. I try to be on my toes. Yeah, that's a great question. So the question was, why do we have x dot instead of x prime dot? Okay, great question. Yeah, the reason is the structure of the calculation was this one here. We're integrating from x1 to x2. And this was completely general. The locations x1 and x2 could be 2 points. Again, it gets a little weird if you exchange the locations. If x2 is to the left of x1, you have to worry about a minus sign. But for what we're doing, let's think of x1 as in our original picture here, and x2 over here to the right. Okay. So then we showed, using this line of thinking, this is good old distance equals rate times time. How much time elapses traversing a differential distance dx? Well, you must divide by the rate. So it's distance equals rate times time. This quotient gives you the differential time to travel across this distance x. Okay, so what happened here, it was just a renaming. We renamed x2, right? We're always free to dream up the names. And this x2 was the name we had chosen for a point. Suppose we chose the name x for that point, okay? Perfectly okay, all the logic still goes through, but we must use a different symbol. We have to use a different symbol for the variable of integration. So now x prime is our variable of integration, and x dot, okay, what I'm going to do is recycle this formula. We have to put the prime here. Can I squeeze it in? Maybe like so. That's supposed to be a prime, and I really kind of squeezed it in yet. But now this formula is to be used here. Yeah, so that's a great point. So x dot is a function of x prime. So let's, that's an excellent remark, and let's conclude the remark by saying here, x dot is a function of x prime. And I think I should really emphasize this with some red color. Yep, excellent question. I've used red color here to identify. We have notation that captures this concept that x dot is a function of x prime. Here's the formula with the square root here in the lower left. This is an example, right, for the motion of a particle in the presence of a potential. And x dot is a function of x prime with the understanding that x prime is the location of the particle. Yep, so great question in the chat window. And the answer is that x dot is now a function of x prime. Now let me reread the question to make sure I've answered it. Why do we still have x dot instead of x prime dot? Yep, great question. So the answer is that x dot, now you could have called it, right, you could put in another layer of notation. You could say this is x prime dot, but we can stay with the original, right, our original space. The motivation is that the physical space was x, right? We had the x-axis here, and we use x dot for the velocity. That's right. So there are lots of great questions here with the notation, and this has been an interesting discussion. Now let's talk about a higher dimensional example. There are some fascinating things that happen when we go to higher dimensions. Let's get some more paper here. Okay, so we'll talk about this fascinating higher dimensional example, and then we will talk about logistics for the course. Remember, we must discuss the logistics. We have to talk about exams. We have to talk about homework, all that stuff. We got to talk about that. This morning I did upload a new version of the syllabus with some details, but I wanted to verbally go through it. But I'm just so excited about the physics, I just won't shut up about the physics. And yeah, we'll get to the logistics in a moment. Let's talk about some higher dimensional examples. So there are two theorems. Okay. Okay, so actually, before I talk about the theorems, let's talk about Zoom for a second. All right. Again, the university decided that we're going to use Zoom. It wasn't my decision. And there are some people that are concerned about Zoom and like, does the Zoom software have access to your data, that kind of stuff? But more specifically, we should not force students to share their names with other students. So in Zoom, you can actually change the name. So if you don't, you don't have to display your personal name and have it visible to other students, right? That's actually against the rules, so to speak. We can't release the names of one student to another student. And furthermore, for the chat window, if you have a question, you can send it privately to me, and then your name is not displayed to the other students. And the other thing I want to mention is I am recording the lecture, but I do not upload, Zoom prepares a summary of the chat window. I don't upload that because, again, it has students' name. That's personal information. I'm not supposed to upload personal information. Over the recent spring semester, maybe some of your other instructors did that. They probably weren't thinking about this issue of personal data and privacy. So I think you're going to see that practice kind of fade away because we're really not supposed to release students' names to other students. Yeah, so in the chat window, you can privately ask me a question and I see the question, and that's what happened here. A student asks a question. You're also welcome to ask publicly. Some students are perfectly happy with it. Both are perfectly great. Whatever you choose, it's a wonderful choice. So we're going to talk about these two theorems because we had a very interesting discussion. We saw that just one-dimensional motion, a particle moving along a straight line, right? We saw there was quite a bit to say about the functional relationships. Now, if you increase the number of dimensions, all right, then, oops, that was not an earthquake. I just bumped the table here. Let's talk about these two theorems. We get some interesting stuff going on. So the reciprocal theorem okay, that's the one we just talked about. We're going to use some slightly different notation. Again, we have to be able to adapt to, if you're reading some of these papers that we talked about earlier today, different authors will use different notation. So we have to adapt to different notation. And then, so there's this reciprocal theorem that's essentially what we just talked about. If you have a function of a single variable and you look at the inverse function, so maybe you have tangent, the inverse of the tangent is the arctangent. You can write down a nice formula for the derivative of the arctangent, etc. So I'll fill that in a second. And then the so-called reciprocity theorem. Okay. So this reciprocity theorem, wonderful theorem here. We're going to have a lot of fun with this. Okay, so that's the remarkable thing. This is -1. We're going to go through this in a little more detail. Let me just talk about the relation here. The reciprocal theorem, and I'll explain this notation in just a second, is dx dz at constant y. Okay. So we're going to talk about these theorems. And again, the remarkable thing is this -1 here. And we'll go through an example. So first of all, let's understand the notation. We are talking about partial derivatives. For this lower theorem, for the reciprocity theorem, there are 3 variables. It's truly a 3-variable thing. For the upper theorem, notice both of these are at constant y, and I should say, this is notation from thermodynamics. It is also used in classical mechanics sometimes. We're computing a partial derivative here. It's understood for this derivative that x is a function of y and z. Okay. For this first derivative, x is a function of y and z, and we compute a partial derivative. Okay. You're going to hold z constant. So we're going to compute the partial derivative with respect to y. Again, that's a function of y and z. And we're going to have a constant here. Okay. Oops, I went off the paper. So all of this stuff here, let me make that arrow better. Okay. So you see what we're saying here. This is notation. The mathematical setting here is we have a relationship between 3 variables. How do we visualize a relationship between 3 variables? Again, it's important to visualize, to have a mental image here. So for the reciprocity theorem, it is a picture like so. Okay. For the reciprocity theorem, we have some sort of relationship between 3 variables. How can we visualize a relationship between 3 variables? Well, you should think of some sort of surface in a 3-dimensional space. So now I'll use pencil here to try and, I'm drawing an arbitrary, well, I love pencil, man. It's so much better than that gel pen. I'm really glad in art classes they have like charcoal drawing and stuff like that. This is the best thing ever. Okay, so yeah, what I'm trying to do here is draw, this is an arbitrary surface, okay? So for the reciprocity theorem, we have a relationship between 3 variables, okay? And we're gonna work through an example. Let's do an example here because my guess is there are some of you that don't believe this is a -1, and that's good. It's good for you to question authority, right? And all those words. Because if you look at this, you could just cancel, there's a dx canceled against that dx. There's a dz, cancel against that dz. There's a dy, cancel it. It sure looks like they all cancel out and you should just get 1. Let's do an example. We'll do a paraboloid of revolution. This is a paraboloid of revolution, so we'll just have z. Okay. And here we're doing pure mathematics, right? Because if these had dimensions, we'd have a problem. X squared would be in square meters. That clashes with the units here, that's in meters. But for this discussion, it's pure mathematics. These are dimensionless quantities. And then it's okay to say z equals x squared plus y squared. Okay. So the picture would look like this. Can I do it? Yeah, because I brought my traditional pencil, which is a really good way if you need to do free form. And I'm trying to draw a paraboloid of revolution. You kind of have to just go for it. And just, anytime you're drawing a paraboloid of revolution, just start doing this. Okay. Paraboloid. That's our paraboloid of revolution. This is our example. Okay. So again, the reciprocity theorem is very general. This is the general statement. This was intended to be an arbitrary picture, right? Because we have a very general, this is supposed to be just some surface somebody dreamed up, an arbitrary surface. Okay. For the example, it's useful to go through this very clearly. So if z is x squared plus y squared, then what is x as a function of y comma z? We have some explaining to do, right? Let's figure out what is x as a function. That means we solve, and again, locally, we'll choose a positive branch. So locally, x is, you got a z minus y squared and the square root thereof. And again, the notation, to really be clear, this is x as a function of y comma z. Okay. So now let's compute the derivative. We're going to hold z constant. We're going to differentiate with respect to y. And again, this is a stylized lowercase d. This is not a lowercase delta. A lowercase delta has a loopy thing that goes the other way. This is a stylized lowercase d to indicate partial differentiation. Okay, can we figure out this derivative with respect to y? Sure, we're going to use the chain rule. We're differentiating something to the 1/2 power, so the partial derivative of x with respect to y. Okay, now notice this notation here is coming to us from thermodynamics. It's customary to really emphasize which variable you're holding constant. Because in thermodynamics, there are all these variables like the Gibbs free energy, the Helmholtz function. It can get confusing. So in thermodynamics, they really emphasize which variable is being held constant. But in this context, if you have x as a function of y comma z, then if you compute the partial derivative with respect to y, it's really redundant to say we're holding z constant. So it's acceptable to not write the z. Okay, so here, that's what I've done. The derivative of x with respect to y, holding z constant. Okay, so we have this thing to the 1/2 power, we're differentiating, so that's a 1/2. We have the 1 over the square root of z minus y squared. And then the chain rule says we must differentiate this thing with respect to y minus 2y. Okay, so that's an example here. Okay, so let's summarize this. You could go through this, and I would recommend you do this as a nice exercise to compute all the derivatives, right? So certainly this one here, dz dx, that means we're going to differentiate with respect to x, holding y constant. Well, we should just do that right now because that's easy, right? Z is x squared plus y squared, so dz dx (2x). All right, and you can see why I crossed my z's. That's clearly a z. That's the number 2. You have to be careful in this business. Okay, so you can go through the rest of the calculation and convince yourself that this theorem is correct, and you do get this remarkable -1 here. Okay, so a couple of things are to be said here. We're going to use this theorem here with the -1. We're going to use this later in the course. Our main interest today is understanding functional relationships. Okay. For the reciprocity theorem, you necessarily have 3 variables, right? X, Y, and Z. You see, for the reciprocal theorem, you don't need to discuss it in a 3-dimensional context. You can if you like. And then Y is a constant here, and Y is a constant here. In other words, Y is simply a parameter like K. You know, K could be a spring constant, something like that. M, the mass, those are constant, elementary charge. So for the upper theorem, for this reciprocal theorem, you're really not necessarily in a 3-dimensional space. You can just declare that this Y is a constant parameter, and then you're back analyzing the relationship between 2 variables. Those variables are now X and Z. And you have this statement that the derivative of X with respect to Z is the reciprocal of the derivative of Z with respect to X. All right, so this is the well-known result that we used earlier today in our discussion of 1-dimensional motion. Later, when we do Hamiltonian mechanics, we'll be making use of this relationship. And this minus sign is going to be very important to us. All right, so that's the theorem. Okay, let's talk about some course logistics. All right, so summer. Okay. Oh, wait, we got a question. Does the reciprocity theorem hold in 3D? Yeah, that's a great question. In other words, if you had a 4-dimensional space, let's say you have W, X, Y, Z, 4 axes, and if you have some sort of relationship between these 4 variables, how could you visualize that? Well, this would be very difficult, right? Because you're visualizing a 3-dimensional surface in a 4-dimensional space. That gets to be complicated. But you could introduce notation for this surface, and then there's a problem that occurs here. For the 3-dimensional case, notice if you have 3 variables, then you can write X as a function of Y comma Z, for example, and then start computing derivatives. But if you go to 4D, and I'll put that, let's talk about the 4D case here. We'll put a question mark here. It's a great question, and it would launch us into some kind of research topics, right? In other words, we're going beyond the course. What would you do in 4D if you have variables W, X, Y, and Z? Okay, how would you arrange this? Well, you could solve for W as a function of X comma Y comma Z. Okay, and now you see there are several derivatives you can contemplate. You can contemplate, once you have that, partial W with respect to X, for example, holding both Y and Z constant. Okay, so yeah, for today's lecture, you know, it's an excellent question. How do we go beyond 3 dimensions? The point we want to make is that you have a great number of derivatives. You could look at the derivative of W with respect to X, W with respect to Y, W with respect to Z. So that's what I'm indicating here with these arrows. And yeah, it turns out there are many different generalizations, right? How many things do you want to multiply together? So yeah, that's a great question. We can maybe talk more in office hours and something like that, because it would really get us into a lengthy discussion. Okay, yeah, excellent question. And yeah, let's resume. We can pursue that in office hours or discussion section. Okay, but we need to talk about the course logistics. In particular, if you have a conflict with our exam dates, then we need to address this as soon as possible. So here's what's going on with our course. We have 11 homework assignments. We have 11 homeworks. We have 2 midterms. Oops. and we have one final exam. Okay, so here's what we need to talk about in terms of the logistics. What happens is, as you know, this is an 8-week session. We have to cram the entire course into 8 weeks. It's kind of crazy. Some people would say we're crazy, but we're not. We can do this. But the point is, it's going to be a very intensive summer session. During a regular semester, a spring semester, a fall semester, you have the luxury of 15 or 16 weeks. That's a lot of time. During the summer session, we're going to do all the same material. The summer session is not a free ride. We're not going to reduce the amount of material in the course. We're going to do everything that's required during our normal semester. But you see, we're going to have to work twice as fast. In particular, it turns out that our usual homework cycle is going to be a 4-day cycle. Every 4 days, on average, we're going to have a homework assignment due, okay? And I talk about this in the syllabus. A 4-day homework cycle is a little bit scary. I publish the homework, and it's due approximately 4 days later. There are going to be some fluctuations in the schedule, but we have to do that. It would not be a good idea for me to publish the homework earlier, because it's really not good for you to start the assignment before we've really introduced it in lecture. Okay, so I won't be publishing the homework earlier. And also, it's not a good idea to start pushing back all the due dates, because then you just take away from the time for your next homework assignment. Yeah, so the upshot is we're going to have a 4-day homework cycle. And let's talk about this. Where did my notes go? Oh, yeah. So homework 0, you know, homework 0 is just kind of a practice. You don't hand it in. It's just for your own benefit. Homework 0, I published it this morning, and you should think of doing it kind of within 4 days to get into the usual rhythm here. Now, homework 1, I'm going to publish soon. It's going to be due Sunday. Okay, Sunday, all right. Okay, so that's the situation with homework. Homework 1 is the first real homework assignment. And I will publish it soon, and it's going to be due Sunday, because we're kind of just starting up the course here. The schedule at the beginning of the course is a little bit different. But our usual homework situation will be due Tuesdays and Fridays. Okay, let's talk about the exams. So the midterms, we have our midterm 1. So first midterm, we have our second midterm. Okay, here's what we're going to do for the midterms. The first midterm is on the Friday at the end of week 3. Okay, so the end of week 3, give me a second here. Let's do this. Yeah, you can see this is not your ordinary calendar. By no means is this your ordinary calendar. We've got June, July, and August of 2020. I have arranged them like this so we have continuity. There are no gaps in this calendar. That thing right there, the July 4th holiday is going to be celebrated on Friday, July 3rd. Okay. So the first midterm is on the Friday at the end of week 3. That's July 10th. And then here's week 6. Okay. We're looking at, oh, I might have put this wrong in the syllabus. Okay. I just, in the back of my mind, I might have put this wrong. Anyways, you see the Friday in week 6, that's the 31st. Okay, now here's the thing. We have students located around the globe. So if we have only one time for the midterm, it's unfair to students that would have to get up at 2 in the morning or something and take a midterm. You would not be in top form. So for these exams, there are 2 times. Okay. So for those of us in California, right now we're on Pacific Daylight Time. Okay. And in the syllabus, I describe for this first midterm, there are 2 times. One of them is kind of a morning time here in California, and the other one is 12 hours later. Okay, so the idea is with these 2 times separated by 12 hours, anyone in the globe, it's only those people that sleep more than 12 hours a day. They might have a problem with this exam idea, but most of us don't sleep 12 hours a day. So the idea is with 2 time slots, everyone on the planet should be happy with their exam. We must use the honor system. It's the same exam. So it's very important that the students who take the exam in the morning session, what we in California call the morning session, you cannot tell other students what's on the exam. Right? The honor code is very important for everything we do here. And we really have to adhere to the honor code. So no sharing the exam. Then after both of these, you see the 2 times for the July 10 exam. After we've concluded the exams, then I will post the exam on B-Courses, and then you can discuss it. Same thing for the July 31st. Again, for those people in California, you would say there's a morning session and another session 12 hours later. So you choose, you have to choose one of those sessions for the exam. Final exam, same idea for the final exam. Okay, so the final exam is going to be on the Thursday. And the reason is, historically for these summer sessions, some students have had issues with a Friday after the session is over. So we don't want to have an exam. We don't want to have the final exam on the Friday after the session. So it's August 13th, Thursday, August 13th. Okay. Yeah, so that's a summary of what we're doing here. So please let me know. You can send me an email or something like that. If you have a conflict, we need to know about it. But the idea with the 2 time slots is we can accommodate people around the globe. And I know some of you have work schedules. So if you have work schedule, we can accommodate that. It should be possible to make this work. So yeah, the details are in the syllabus. Again, homework 1 will be published soon, and then it's going to be due Sunday. That's unusual because our usual homework cycle will be Tuesdays and Fridays. Okay, so that was the course logistics. Now we have 4 minutes left. We're going to do some more physics. All right. Oh, I forgot to mention the reading assignment. The reading assignment for the near term. Okay, how long will each time slot be for the midterm? Oh yeah, great question. We got a question here in the chat window. So for the midterm, it's 1.5 hours. Okay. So the midterms are 1.5 hours, and the final exam is 3 hours. And you get the full 3 hours. Yeah, great question. So oh, here we go, another question. Is the class going to be graded on a curve, or are there set percentages? Oh, that's an excellent question. We have a question here in the chat window. Is the class graded on a curve, or are there fixed percentages? Okay, so that's an excellent question. Let me ask the vice chairman, because You know, the spring semester was very special, but now we're transitioning back to kind of our usual state of affairs. So traditional grading, where you have fixed percentage, for example, traditionally 90% and above would be an A, between 80% and 90% would be a B. That's traditional fixed percentages. On the other hand, a curve, traditionally this course is graded on a curve and 35% of the students get an A. Okay, that's traditional curve grading. So I will check with the vice chairman and then I will report back because that's an excellent question. So this is on my to-do list. We need to answer this question here. Okay, yeah, great question. So that's on my to-do list and I will report back with the answer. Okay, so the reading assignment. Let me tell you the reading assignment. Okay, this reading assignment now, together with the philosophy, kind of what we're doing in this course, we're basically starting in chapter 5. Okay, so start in chapter 5 and read up to page 180. Go to page 180 over the next 2 or 3 days. Okay, so let's talk about this reading assignment, and I want to put some red color here. So I use some red color here for the reading assignment. Let's talk about this. Where are we going? What are we assuming? So we're assuming some familiarity because you've taken the 7 sequence or the 5 sequence, right? Very nice sequence in first year physics. So we're assuming you're familiar with the topics in chapters 1 through 4, except for a few pages that I indicated are difficult, above the average level of difficulty. So what we're going to do here is we will review some of that material, especially in the discussion section. We're going to review the material in chapters 1 through 4 that's more difficult. Basically, in terms of our summer session, we're going to start in chapter 5. Okay, so the reading assignment is start at the beginning of chapter 5, go up to page 180 over the next 2 or 3 days. At that point, I will give you another reading assignment. But for the near term future, this is our reading assignment. We're going to be working in chapter 5. Some of this stuff is review, right? Because I know that in the physics 7 sequence and the 5 sequence, there's quite some discussion of the damped oscillator. Okay, so that's your review. Okay, but a lot of this discussion, for example, we're going to revisit this now with real emphasis on understanding the functional relationships. Okay, wonderful. So what I'm going to do here, I'm going to stop the recording. I will stay here for a while to see if you have any questions, but let me see if I can. Oh yeah, we had a question here. To submit homework, we're going to submit on B courses, and I will prepare a so-called assignment, a B courses assignment, and you're going to upload a PDF file. Excellent question. I'm going to, you know that it's not easy for me to find this. I have to resize the window to even get to the button. Yep, there it is.